Hi everyone. In this talk, I'm going to introduce our recent work in using hyperproperties for robotic plannings. Specifically, I'm going to introduce what is hyperproperties and why they are important for robotic plannings. In addition, I'm going to introduce how do we formally express hyperproperties using a temporal logic called HyperLTL. Finally, I'm going to introduce how do we synthesize plans for objectives that are expressed using by HyperLTL specifications. To begin with, let me introduce some basics on using temporal logic in specifying planning objectives in robotic planning. The most commonly used logic is probably the linear temporal logic. It is a set of 5 rules, and using these 5 rules, we can express a wide class of planning objectives. In LTL, we have atomic proposition, negation, conjunction, and the next temporal operator, meaning that something should happen at the next time instance on a path, and the until operator, meaning that something should happen until another thing becomes true, and this change should happen before the time bound t. Using these 5 rules, we can express common planning objectives such as something finally happens on a path, or something always happens on that path. We note that linear temporal logic is originally defined for infinite paths, but it can also be used for finite paths if we view them as a special case for an infinite path. And in robotic planning, we are usually more concerned with finite paths. Therefore, we consider the finite time fragment of the linear temporal logic. This finite time fragment is derived by setting the time horizon t in the until operator to be bounded, and we call this finite time horizon fragment LTLF. Having expressed the planning objective in LTL, basically the planning problem is to find a path pi such that the LTL formula phi holds on that path pi. So our main problem with the linear temporal logic is that it cannot express hyperproperties. A hyperproperty is basically a planning objective that implicitly or explicitly involves multiple paths. Such properties cannot be expressed by linear temporal logic. Here is an example. It is a planning problem with privacy or opacity objective. Specifically, consider the problem of synthesizing a path from a start region to a goal region. At each time, the position of the robot is not directly observable, but we can tell whether it is at region A or at region B or at region C. Then the opacity requires that for the synthesized path pi, there exists another path pi prime, such that both paths yield the same partial observation. Therefore, we cannot tell exactly whether the exact synthesized path is pi or pi prime. Similar examples are opacity and robustness. So the synthesized path pi is optimal if for any path pi prime that reaches the same goal, it takes a longer time. And the robustness basically means that for any path pi prime that is derived by perturbing the path pi, the design objective is still satisfied. So we have seen that there are many important robotic planning objectives that are hyperproperties. For example, opacity, optimality, and robustness. To formally express such hyperproperties using temporal logic, we need to extend the linear temporal logic, and this logic is HyperLTL. So the HyperLTL has been proposed in the past few years by the formal method community, and here we use them to specify planning objectives for robotic planning. So HyperLTL extend LTL by introduce a set of path variable. So each path variable denotes a different path, and we associate these path variables with the atomic propositions to indicate that these atomic propositions should be satisfied by the path pi. In addition, HyperLTL allows universal and existential quantification for the path variables. To evaluate the correctness of a HyperLTL objective, we just need to assign a concrete path to each path variable, and the interpretation for the existential and for all quantifiers are interpreted in the common sense. Using HyperLTL, we can express planning objectives that are hyperproperties. The first example is optimality. Specifically, we can express the shortest path from the state S0 to some goal set using this HyperLTL formula. Similarly, we can express the longest path from S0 to G for some implicitly given bounded time horizon. Another example is the robustness. Here we consider two kinds of robustness. The first one is the initial state robustness. It means that the synthesized path should satisfy the objective phi even if there's a perturbation on the initial state. The second kind of robustness is the action robustness. It means that the objective phi should be satisfied even if there is a perturbation on the action for one time instance. Finally, we can express opacity using HyperLTL. The first kind of opacity is the initial state opacity. It means that there are two paths with the same sequence of actions but different initial states that yields the same observation. This basically means that the initial state is kept opaque under the observation. Similarly, we can express action opacity. It means that there are two passes from the same initial state but different actions that yields the same observation. Therefore, the sequence of action is opaque under the observation. We have seen how to use HyperLTL to specify plenty of objectives that are hyperproperties. Now I'm going to demonstrate how do we use SMT solvers to synthesize plans for those objectives. Specifically, we consider the finite time fragment of the HyperLTL, namely the HyperLTLF. We follow the following three steps. The first step is to get the time horizon for each path variable. This is because we are considering a finite time fragment. Therefore, we only need to keep track of finite steps for each path variable. And the time horizon can be identified using the following inductive rules. For example, for this optimality objective, we need to keep track of path pi1 for 2t time steps. The second time step is to decompose the path quantification into a sequence of quantifications over states and actions. This is because a path is uniquely determined by its initial state and the sequence of actions. Therefore, for example, a universal quantification over the path variable is equivalently a sequence of quantifications over the states and actions. So after step 1 and step 2, actually the HyperLTLF's objective is converted into a first-order logic formula, and such a formula can be solved using the off-the-shelf SMT solver such as Z3. Now I'm going to show the result of several case studies. These results are derived by our SMT-based synthesis algorithms for HyperLTL objectives. The first case study is on optimality. Specifically, we would like to synthesize the shortest path from some starting sets to a goal set on a grid world with obstacles. We've performed this case study on both 10 by 10 grids and 40 by 40 grids. The time for 10 by 10 grids is in a few seconds, and the time required for synthesizing the plan for 40 by 40 grids is a few minutes. This figure shows the result for the synthesis on 10 by 10 grids. The starting set is given in red color, the goal set is in green, the obstacles are in black, and here we shown two shortest paths. The second case study is on the robustness. We consider both the initial state robustness and the action robustness for some reachability problem, again on a grid world with obstacles. Again, we consider both 10 by 10 grids and 40 by 40 grids. The time consumption for 10 by 10 grids is a few seconds, and the time consumption for 40 by 40 grids is a few minutes. Here are the results for the synthesis for initial state robustness and action robustness for 10 by 10 grids. Our third case study is on opacity. Specifically, we consider both initial state opacity and action opacity. This synthesis is performed on a grid world with obstacles for some reachability property. We consider both 10 by 10 grids and 40 by 40 grids. The time consumption for 10 by 10 is a few seconds, and for 40 by 40 is a few minutes. Here we show the planning results for the 10 by 10 grids in these two figures. To summarize, in this work, we demonstrated that there are many important planning objectives that are hyperproperties, and to formally express those hyperproperties by temporal logic, we need hypertemporal logics, namely the HyperLTL. In addition, we showed that using HyperLTL, we can express a wide class of planning objectives that are hyperproperties, and the finite fragments of this logic, HyperLTLF, can be solved using SMT solvers. We also would like to emphasize that even although in the case studies we consider a discrete planning problem, actually SMT solvers can also handle continuous problems, and this is for our future work. Finally, I would like to thank you for your attention, and if you have any questions, please feel free to contact us via email.